To follow Gene on this because he's already mentioned several times in his talk geochemical proxies, and what I want to do today is sort of a broad introduction to what my group has done and will continue to do now that I've moved here, is address some of the newer geochemical proxies and related work that we're doing in terms of the optimism, pessimism, realism scale, which I'll show in a second. But first of all, just to kind of step back a little bit for those of you who aren't familiar with the geochemical literature going back this far in time, is just what is a proxy? Okay, probably the most common reference to a proxy is anybody who has a stock retirement plan gets proxy voting mail, and you know, maybe we don't even know what that means. I generally don't, but a proxy is basically an indirect measurement, and it's a way, in terms of your stock plan, it's a way you can vote without being in the boardroom. It's an indirect measurement of some sort of a condition or an indicator of some sort of condition. In geochemistry, especially in marine geochemistry, we're interested in conditions of the ocean in the past. And these are ephemeral conditions, ephemeral states, but what we're looking for as geochemists are sort of the fingerprints of these events and conditions. And proxies themselves are nothing new. Does this have a laser pointer on it? Yeah, there it is. Okay. You know, I put some sort of general decadal scale times of when they come about, but some of the things that we're interested in are like temperature of past ocean water, salinity of the ocean water, sunlight and cloud cover, nutrients in the water column, stratification of water masses, even presence or absence of currents. These are all sorts of things that we can get at using geochemical proxies. They're not great measurements. I'd be the first to admit that. You know, if you wanted to measure the temperature outside right now, you probably wouldn't hold a coral out the window. You'd probably just, you know, look at a thermometer or something. But we're trying to go back in time since before good measurements were made, as Gene was talking about, well into the past. So all of these proxies, to get at these different conditions and states of the Earth, are different in the way we apply them and what we actually measure. The fingerprints are all different. But one thing is the same, and that's this sort of phase diagram that proxies go through. And this is sort of what the community's opinion of a proxy is from its inception to its widespread use, okay? And what happens is when somebody comes up with a new proxy or a new way to fingerprint past conditions, you have this very nice optimism phase. And this is where everybody is really excited, like, wow, you can tell the temperature of the ocean in the past, and everybody wants to jump on the bandwagon and start measuring this proxy themselves. And of course, when that happens, the warts are exposed, okay? And we start to ride this roller coaster down into the pessimism phase, and people start to realize that, well, this is not behaving as theory would have had or as it was originally presented. But eventually things generally get worked out. There are times, by the way, that the pessimism phase can kill a proxy. That's for sure. But in most cases, we end up coming to some realism phase that's somewhere south of the optimism phase. It's very rare that the realism phase exceeds the optimism phase. But this is the general, there's no units on the x or the y-axis. This is all relative, right? But I want to kind of go through some of the work that we do in our lab, and it's very new, and kind of assess where we are on in this diagram. And what I'll talk about is I'll kind of divide the talk into two here, and we'll talk about clumped isotopes of CO2 that comes from calcium carbonate. This is a temperature proxy, which is on my list earlier was one of the older ones. But what's interesting about this is it's one of the few temperature proxies that has been brought forth that is independent of isotopic or chemical composition of the water in which things were precipitated. So it has a lot of potential upside in its use, and it has generated a lot of optimism in the early going. And then I'll get into my work in ramp pyrolysis C14 dating, which in and of itself is not really a proxy, but it's important to note that anytime we want to do reconstructions with proxies, we need to have a good idea of the chronology of our record, which Gene was just talking about. This technique is founded in that, but we can kind of put it on the same sort of scale of optimism to pessimism to realism and judge where it is based on some of the developments. So basically, the question is, where on this roller coaster are we, and who's willing to ride it with me? If you're a student looking for an interesting place to do a study, does anybody have the intestinal fortitude to go down into the pessimism phase with us, which is always fun. But to start, I'll give you a little bit of background on clumped isotopes. This is sort of two systems here. This is a very simplified diagram. It's a diatomic molecule, hydrogen, for instance. So the light colors are a mass 1, and the dark colors are a mass 2 with an extra neutron attached to the proton. And what you can see here is that if you know sort of the bulk composition of how many of these, generally the heavy ones are the rare isotopes in stable isotope systems, if you know how much in an entire system, how many of these are heavy, you can use thermodynamics to come up with statistics on how many of these will bond together. And in this case, we showed two heavy isotopes, rare isotopes bonded together, and we call this a clump of isotopes. It's two heavies bonded together. Okay. What's interesting is that this is generally, this random distribution, or stochastic distribution as we call it, is going to happen at very high temperatures, upwards of 1,000 degrees. On Earth's surface, you're generally going to have more clumping of the isotopes than is predicted thermodynamically. And this difference from the stochastic distribution, where we see a few more of these clumps in this picture, and it's blue representing cooler temperatures, what we want to do is to be able to measure this. Now, the problem has always been, since the 1940s when we've been measuring oxygen isotopes and getting an idea of what the bulk system is, usually these rare isotopes are less than about 1% of the entire pool of isotopes. So the probability of seeing two of those bonded together then would be less than 1/100%, right? So we're talking about measuring exceedingly small signals that are then very susceptible to contamination during the measurement process. But what's interesting about this is that this is a property of the element itself, and it's removed from the bulk isotope composition. So we kind of remove some of the difficulties in making assumptions about the isotopic composition of past water masses in which calcium carbonate is precipitated. And that's really the focus of this is calcium carbonate and other carbonates, and using it in terms of paleothermometry, because that makes up a large portion of our geologic record. So here's sort of a bibliometric analysis in the last few years of if you go to the Web of Science and type in clumped isotopes and weed through a little bit of noise from people who study stars. This is what you get. I don't know where the term clumped isotopes and stars comes from. Maybe you should read some of those. But in any case, the first papers actually came out in 2003, 2004. They weren't really using the term clumped isotopes, so it doesn't come out. In this analysis is very simplified. But what you can see here is a very nice growth. And in 2014, we're already up to 45 papers in this small sort of field. So it's really a big growth. But what's interesting is that when you look at these, the types of applications of the paleothermometer, in the beginning, all of the data were emanating from one laboratory, from one machine, and it was at Caltech from John Eiler's group. And a few years into it, about 2009, 2010, a few of what I call his offspring, his postdocs, went out and created their own labs, and they were all using the same exact methods, the same exact types of machines, and they were the only ones generating data. When you get into this area, you have me and a handful of other labs that are kind of crashing the party, that aren't related to John Eiler in any academic way, and we're coming in and doing things slightly differently. And of course, what happens is, if you look at this, the biggest growth in the last 3 years is in this red box, which is sort of technical or review papers, calibrations. This is kind of exposing the warts and getting down into the pessimism phase here. So if I had to pick a point where we were, and this maybe I'm a little bit optimist, but this sort of bibliometric analysis shows us that we're starting to fall into the pessimism phase. But I'm going to show you some of the reasons why and paint a more optimistic picture at the end. This is the original calibration. So this is back in 2004, a paper that came out that they measured some carbonates, some corals, some otoliths, some soil carbonate, brachiopods, mollusks, and some laboratory precipitated calcium carbonate that was done at certain temperatures. And you see that everything falls on a nice line. We have temperature on this axis, plotted the way that geochemists like to plot it. And on this axis, we have this capital delta 47. 47 is the mass of a CO2 molecule. It has a C13, an O18, and an O16. So that's what we're measuring, are ion beams of that mass. And what this shows is that over a wide range of temperatures, this seems to work. There's a very tight linear relation. And this is what generated the original optimism. This is what got everybody excited about the proxy. All of these were precipitated in different water compositions. We didn't have to worry about what water composition they were. They still fell in the same line. If you were just measuring bulk oxygen isotopes, some of these would fall off of that line depending on an offset produced by the isotopic composition of the water in which they were precipitated. So this seemed really nice. Fast forward to labs like me. This is an example of our, nobody probably cares about this, but I like the picture. This is our cluster of collectors here, Faraday cups. This is the only alteration we made to an isotope ratio mass spectrometer. We didn't do anything fancy to it. Just put in a few other buckets to capture these extra ions at heavier masses in CO2. And we decided that we were going to try to play with the big boys, or John Eiler and his offspring, I guess, and do the measurement ourselves. And fast forward a few years, and this is what we're looking at. We see a calibration now that has a lot more noise in it. And I'll get to the colors and the bands. This is not all from our lab. We have two of the calibrations in this. This is sort of a compilation up to about the springtime of what people had published so far. So again, we're starting to ride into that pessimism phase. When people see this, it's not as exciting or optimistic an outlook as the original calibration. I just had a student, Alvaro Fernandez, publish a paper where we started to look into the reasons for this growing cloud of data that's starting to move away from that original calibration line. He actually did his own calibration on the mineral siderite, which was it's a mineral made of iron carbonate, and it's not been used very widely as a paleothermometer because it's difficult, but it's available in deep time, and it could be potentially useful for us. But he broke down the analysis into laboratories that use a higher temperature acid digestion of the calcium carbonate come up with a flatter slope, and laboratories who use a colder temperature come up with a steeper slope. And the steeper slope is more like the original calibration, but more and more labs are coming up with this flatter calibration. And you can kind of see that this is a breakdown of the raw data. And then I had my postdoc / lab tech, Jin Tang, published a paper where he pointed out that the flatter slopes were actually closer to what theory would predict. So this is kind of an interesting view, but you can see that at this point we kind of feel like party crashers, and that we're bringing the proxy down the roller coaster a little bit. These are some of the summary points of our two calibrations done in our lab, and this is important because originally that relationship to temperature of the acid digestion was assumed to come about as a result of different acid fractionations, and these two minerals, the purple is siderite and the green is calcite. These two minerals are very different thermodynamically. And one would have expected if the fractionation factor was an issue, that these would have plotted much differently. In this case, we haven't even put on a fractionation factor, and the lines are pretty much right on top of each other. So these calibrations of very different minerals are not any different than each other. And that kind of suggests that it actually is more complicated than just the acid fractionation factor. And these are some details on my postdoc / tech's calibration on calcite. And this was a very interesting data set because we had all laboratory grown calcium carbonate that was at a wide variety of precipitation rates that are kind of indicative of all the rates in nature that we know of. We had a range of pHs and a range of ionic strengths, so varying between fresh water and salt water. And what's interesting is that the temperature relationship is pretty robust no matter how we vary these other parameters, with the exception of two very high pHs above 10. These are outliers, and they the temperature equivalent of this is sort of like negative below zero. So it's very unrealistic to think that you would find carbonates in nature of this value reflective of temperature, but it's probably due to this high pH and the way that the rate of precipitation differs from the rate of equilibration between the CO2 species in water. But this is important because some people have started to view these in nature, and you obviously can't interpret them as a temperature signal. But this is a threshold relationship. pH was varied in these points as well, and it doesn't show up as strongly. So getting back to this, this overall it seems pretty pessimistic because of this data cloud, but there's always power in numbers, right? And statistically speaking, the model drawn through these numbers is very similar to the shallower slopes. It's similar to the theory. The temperatures from our one single lab calibration are fairly close. This is on just some replicate analyses of a laboratory standard. The temperatures are fairly reasonable, but outside of the analytical uncertainty. But what's interesting about compiling everybody's data like this is that it shows that we can get into sort of a universal calibration that has its uses not in being able to determine seasonality in a coral or a mollusk, but being able to compare things that may have been precipitated at Earth's surface and then were buried and diagenetically altered. Because we can, if we apply the whole model uncertainty here, which is greatly reduced by the sheer number of samples, of course, we get into lower uncertainties. If you did this with any one calibration that went into this pool, you would have about double the analytical uncertainty if you did the full error propagation, which of course assumes that your absolute temperature is correct. This is the type of error that you're talking about if you want to use it relatively and just compare between the calibrations, where your only source of error is analytical error. So where are we then? I just got back from a workshop actually last week in Zurich, Switzerland, where basically almost all the labs that are measuring this now, 12 or 15 labs, 75 participants though, met, and we just for 3 days really pounded out some of the problems that the labs are having and talked about it, the skeletons in the closet, the ugly warts and everything else, and it's a really good workshop. So my optimistic point of view is that we're going to sort of hopefully have a shallow pessimism phase here. Now this is being said from somebody inside the community, and those of you who are outside the community, maybe when you see those different calibrations, you have a different point of view, and that's what really matters, right, is when we try to apply this proxy, who thinks it works and who doesn't. But hopefully we'll be able to make that pessimism phase a little bit shallower because of the collaboration within the field. And one example is that the oxygen isotope community took about 3 decades to figure out the acid fractionation problems, and we're already working through that in this is only the 4th International Clumped Isotope Workshop. So going fast through this collaboration between laboratories. There's always a bit of competition, but when you do it in this way, it's important. So moving on into the Antarctic sediments and our geochronology, as I said, this is not really a proxy, but it's the basis of using proxies. And this is an example of sediment cores we were taking from Antarctica in 2012 on board the Lawrence M. Gould. And everybody knows that Antarctica was covered with a lot more ice as recently as 15,000, 20,000 years ago. And these are models of ice thickness, and we don't have a lot of data on that. These are models. Interestingly, they're constrained by this black line. It's hard to see. There's a blue and a red and a black line. The black line is actually your geologic evidence for the extent of the glaciers and the ice shelves. And that's really what's used to verify and constrain the models of ice thickness. Because it's some of the best information we have. How far out did the ice push on the continental shelves? If you do a cross-section between the ice shelves, you see the present-day ice thickness in the ice shelves here, which are continentally moored but extending out over the ocean. And you can see the model outputs in these gray lines, which are extending actually outside of the field of view. So, of course, we have more thickness here. That means we have more extent of ice in the ice shelves. So through work that's been done by Jean Domack and Amy Leventer and Amelia Chevenel, we've gotten some of this high-resolution bathymetry, which is hard to come by in this region of the world. And what we see are a lot of evidence of paleo ice streams that are basically the conduits of these, the travel of these ice streams away from Antarctica and back in when the ice shelves retreat and collapse. And you can kind of see the trace of the movement of ice shelves. You can see some terminal moraines. What's interesting is that's just looking at it in the surface. If you look below the surface of the sediment, we get into sort of looking at a sediment core here. And this is published way back in 1999 by Gene Domack. It's sort of an example of a facies one would expect to see from a stepping back ice shelf. And if you start with your sediment core right under the grounding line, you get this sort of glacial sedimentation, poorly sorted, rough. If you stay on the same point but the ice shelf moves back, of course when we have that horizontal movement on the Earth's surface staying on one point, we see it vertically. That's a fundamental geologic law. We see sub-ice shelf, basically if your point moves down here and as the ice shelf backs off, we see sub-ice shelf sedimentation, which can be layered. We see some glacial marine muds as well as some input of marine sediment. And then finally you get to the edge here, you get a calving line of a bunch of debris being dumped out. And as the ice shelf continues to step back, you get marine sediment. And I always joke around that this is a facies that even a geochemist can recognize if he's on a ship. So it's a fairly nice thing to see when you pull up a core and you split it and you say, oh wow, there's a big change there. Geochemists, we only get to see sediments generally in people's little vials that they send to us. And when they invite us on a ship, it's nice to actually be able to recognize even the obvious. But what's perplexing about Antarctica is that the sediments, the time of the deposition of these different facies really is what's necessary to answer these important questions. When did they retreat? How did they do it? Was it slowly? Was it a collapse? How long did it take? And with what global climate events, like what's indicated in ice cores, do these facies correlate with? Well, chronology is the key to applying any of the proxies in these sediments and in these facies to that. The problem is that in Antarctica, chronology is hard to come by because our sort of gold standard is you go and you look for little calcium carbonate shells of 4Ms. You date those using radiocarbon because this is the sort of time span that we're working on. And you get a nice age model. In Antarctica, because there's so much organic material in the sediment, the calcium carbonate is not preserved very well. The shells dissolve over time, and what you're left with is organic material to date. That means that you're susceptible to continental input of organic carbon. There is organic carbon in the rocks of Antarctica because it wasn't always covered with ice, and this carbon is therefore very old. So when that gets mixed in, your organic carbon mixed